Hey, welcome back. Up to this point in the year, we've spent a lot of time talking about derivatives. What is a derivative? How do we find derivatives? What can derivatives tell us? And what are applications of the derivative? Today, we're going to take that and we're going to turn it around. And we're going to talk about how to undo derivatives via a process called anti-differentiation. To find an antiderivative, we're going to take our basic derivative rules and think about undoing them or working backwards through them. Keep in mind, this only applies to our basic derivative rules. At this point, we do not have a way of finding an antiderivative of something that requires the product rule, the quotient rule, or the chain rule. So look at example 1 with me. Consider f of x equals 3x squared minus 4x plus 7, and g of x equals 3x squared minus 4x plus 1. What's f prime of x? Well, using the power rule, I get 6x minus 4. And what is g prime of x? Well, using the power rule, I get 6x minus 4. Notice these were two different functions. Different in what way? They had a different constant on the end, but they had the same derivative because the derivative of that constant is 0. So what's the point here? If I want to take the antiderivative of 6x minus 4, I need to keep in mind that there might have been a constant whose derivative was 0. And can we figure out what that constant is? Without any more information, no, we can't. So if I think about undoing this derivative, if I think about undoing the derivative of 6x, the power rule usually says you take the exponent, you stick it in front, and then reduce the exponent by 1. So now I'm going to take the exponent and increase it by 1, and then divide by my new exponent. Similarly with minus 4, the antiderivative of minus 4 would be minus 4x. And this is the important part. When you take an antiderivative, you have to account for the possibility that there was a constant that got lost. So I'm going to put plus c here to represent plus some constant that might have been lost in the process of taking the derivative. So to simplify this just real quick, I'm going to have 3x squared minus 4x plus c. So the first and biggest idea with antiderivatives is that when you take an antiderivative, you have to include plus c, because you have to acknowledge the possibility that there was a constant that was lost. Example 2, what's the antiderivative of f of x equals sine x? Generally speaking, if we use prime to denote a derivative, we use capital letters to denote an antiderivative. So capital F of x, well, the derivative of what is sine x? That's going to be negative cosine x. So the antiderivative is negative cosine x. But I can't stop there. What do I have to remember? Plus c, because there could have been a constant that was eliminated when we took this derivative. Example 3, what is the antiderivative of ax to the n? So we're going to think of this as being like the power rule for antiderivatives. So we're going to take our power rule process, do it in reverse, which means the exponent is going to go up by 1, and then we're going to divide by our new exponent. So the antiderivative of ax to the n would be ax to the n plus 1 divided by n plus 1, and of course we can't forget plus c. So think of this as your power rule for antiderivatives. The exponent goes up, then divide by your new exponent. So with that in mind, let's look at these 12 problems and just practice undoing the derivative, anti-differentiating to find the antiderivative. And we're not going to forget our plus c. So what's the antiderivative of 0? Well, that would be some constant, c. What's the antiderivative of a constant, a? Well, that would be ax plus c. The antiderivative of ax to the n we just did before. That's going to be a over n plus 1 times x to the n plus 1. The antiderivative of ax plus b, so I'm just taking the last two examples and combining them here. The antiderivative of ax would be ax squared over 2 plus bx plus c. The antiderivative of e to the x, well, if the derivative of e to the x is e to the x, then the antiderivative of e to the x is e to the x plus c. The antiderivative of 1 over x, this one's kind of interesting because if you write it as x to the negative 1 and then try to use the power rule, you're going to divide by 0 and wonder what went wrong here. Well, ask yourself this, the derivative of what is 1 over x? And that's the natural log. There's a small trick here. When you take an antiderivative of 1 over x, it's the natural log of the absolute value of x plus c. And the reason being you can't take the natural log of a negative, so we use the absolute value to cover ourselves there. And now our trig antiderivatives, the antiderivative of sine x would be negative cosine x plus c. The antiderivative of cosine x would be sine x plus c. The antiderivative of secant x times tangent x would be secant x plus c. The antiderivative of cosecant x cotangent x, be careful with your positives and negatives here. We're used to saying the derivative of cosecant is negative cosecant x cotangent x. So because this is positive, the antiderivative is negative cosecant x plus c. The antiderivative of secant squared x would be tangent x plus c. And cosecant squared, again, watch your signs here, the antiderivative of cosecant squared would be negative cotangent x plus c. So this sort of encapsulates a lot of our basic derivative rules that we can now undo and turn into antiderivative rules for the purposes of finding antiderivatives. Real quick before we move on, how do you denote that you want to take an antiderivative? We use ddx or ddt to denote taking a derivative. To take an antiderivative, we write the expression like this. Now, what do these symbols mean? At this point in your life, here's what I want you to understand. This tall curvy s and this dx are buddies. They go together, and whatever's sandwiched between them is what you're taking the antiderivative of. Does this tall curvy s and this dx have a meaning? Yes, it does. You'll learn about that in just a few topics. So for now, just think of them as bookends. Anything between, you're going to take an antiderivative of. So in example 5, I look between my tall curvy s and my dx, and I see take the antiderivative of the cube root of x plus 2x to the fourth minus 1 over 3x. And just like with derivatives, I want to rewrite this problem in a way that's nice and easy to work with. And when I say that, I really mean write it in a way that uses exponents and not square root signs. So I'm going to rewrite this problem as the antiderivative of x to the 1/3 plus 2x to the fourth minus 1/3 times 1 over x dx. And in doing so, now I can take this antiderivative a little bit easier. The antiderivative of x to the 1/3, let's think about our power rule for antiderivatives. The exponent goes up by 1, so I've got x to the 4/3, and then divide by your new exponent, so divided by 4/3. Plus the antiderivative of 2x to the fourth, 4 goes up to 5, divide by 5, so 2/5 x to the fifth, minus 1/3, just like with derivatives, coefficients are along for the ride. What's the antiderivative of 1 over x? That's going to be the natural log of the absolute value of x. So minus 1/3 ln absolute value of x. Am I done? Nope. What am I forgetting? Plus c. That answer is fine. I do want to point out this very first term you could rewrite as 3/4 x to the 4/3, but the rest is fine. And there you go. Example 7 says if h double prime of x is 36x squared minus 2, h of 0 is -1, and h prime of 1 is 12, find h of x. So I'm sitting here at the second derivative, and I want to work my way up to the original function. So this is going to require 2 antiderivatives, and because I was given 2 initial conditions, I can solve for c at both steps. So I'm going to be able to find h of x without any plus c's. So here we go. H prime of x is the antiderivative of h double prime of x, which is going to be the antiderivative of 36x squared would be 36x cubed over 3, so let's call that 12x cubed, minus 2x plus c. Let's pause and solve for our plus c using this initial condition that h prime of 1 is 12. H prime of 1 would be 12 minus 2 plus c has to equal 12. Well, 12 minus 2 is 10, plus 2 is 12, so c is 2. So I know that h prime of x is 12x cubed minus 2x plus 2. And we take it another step. H of x is the antiderivative of h prime of x, which would be the antiderivative of 12x cubed would be 12x to the fourth divided by 4, so we'll call that 3x to the fourth, minus 2x squared over 2, we'll call that x squared, plus 2x plus c, and again I'm going to solve for this plus c using my initial condition that h of 0 is negative 1. So h of 0 would be 0 minus 0 plus 0 plus c equals negative 1. Well, that's easy. C equals negative 1. So my final answer, h of x, is 3x to the fourth minus x squared plus 2x minus 1. So your antiderivatives will always have a plus c unless you have an initial condition that you can use to solve for that c. All right, on to some AP problems here. 2008 AB number 13, take the antiderivative of x cubed plus 1 squared. Well, I see this as a function with layers, but we don't have an antiderivative rule for something that looks like chain rule like we might have for derivatives. So really my only recourse here is to FOIL this out and then take the antiderivative part by part. So I'm going to rewrite this problem as the antiderivative of x to the sixth plus 2x cubed plus 1. That's just from foiling. And now I can take the antiderivative piece by piece. So the antiderivative of x to the sixth would be 1/7 x to the seventh, plus the antiderivative of 2x cubed would be 2x to the fourth over 4. 2 over 4 is 1/2. So 1/2 x to the fourth plus x plus c. And looking at my answer choices, only 2 of them start with 1/7 x to the seventh. So if you got that far, then you've already narrowed it down to 2 options. And answer choice B is my correct answer. 2012 AB number 3. What is the antiderivative of secant x times tangent x? So this is just a basic trig antiderivative. Do you look at this and recognize secant x times tangent x as being the derivative of secant x? Just don't forget your plus c. The answer is A. So to recap, we can find antiderivatives by undoing our basic derivative rules, but we don't have antiderivative rules for things like the product rule, the quotient rule, or the chain rule. So we have to work those out by simplifying the problem as much as we can. After today, we're going to take this idea of antiderivatives and we're going to shelve it for a moment, and we're going to go talk about a seemingly unrelated topic, finding area under a curve. We're going to talk about that for a few topics, and then the fundamental theorem of calculus is going to take these two seemingly different ideas of antiderivatives, area under the curve, and marry them together. So take this idea of antiderivatives and just hold on to it for a little bit, and we'll come back to it in a few videos. I hope that helps. Thanks for watching.